Howdy AP Statistics, and welcome back. We're talking about quantitative data again. This time we're talking about describing the center and describing the spread. So when we're thinking about the SOCs, we talk about shape, outlier, center, and spread. So today we're going to talk about center and spread, and hopefully we have a little bit of time at the end. We can talk about outliers as well. There's a couple of key equations there that help us define when we do in fact have outliers. So I know that most of you have experience with mean, median, and mode. So I'm not going to spend a lot of time reviewing those. Just real quickly, reminding us that, as far as the three M's go, right? Median, right? That's the middle data point. And we'll go through an example here in a minute of how to find that. If there's an even number of data points, there isn't actually a middle data point. You're just going to average the middle two. So a good reminder there. The mode, well, that is, of course, the most frequent. Not every data set has one of these frequent data point. So if you get a repeated data point with multiple times, then that would be your mode, the one with the most repeats. And then the mean, which is another name for the average. And so mean, median, and mode, or these ones are the three measures of center that we're going to be dealing with here. As for this last one, the mean, there's actually a formula that I'm going to write out here. And it's going to use a notation that maybe you've seen before, maybe you haven't. For the average of a data set that's a sample, we have this little X with a bar over it. We actually call it X bar. And what we're going to do is we're going to use this Greek letter sigma. And we're going to add up each of the data points. So the sum of the X's, okay, that's what that means. That means the sum. So we're add up all the X's and divide by the number. So that's what, remember, average, that's what we're talking about. That's all that is. But this is a little notation that you need to know for the mean. The median and mode, we'll just write the words median and mode. But for the average, I wanted to get you that notation so that you have the, first of all, the sigma notation. That's the Greek letter sigma, and that means sum. Some of you have seen that before, others that's probably new. But anyway, I wanted to get that notation down for you. So we're going to take a look at a data set. This stuff is best explained with data. So what I'm going to do is take us over to a different screen. And we're going to be looking at a data set that when I got my first house, I lived in a place, and it was called Kiwi Court. That was the actual name of it. And in a Kiwi Court, it was a big cul-de-sac. But basically it just had 14 houses kind of around a cul-de-sac. And so, if I were to draw the cul-de-sac, here we go. You drove in, there was a road that you drove in on down here. And then you basically had your houses all around the cul-de-sac like this. Well, there were 14 of them, so let's put a 14th one over there. And I lived over here in house number 7, actually. And so what I want to say is, if we had everybody in the neighborhood that made basically the same, it was a very similar. Everybody has similar jobs. We all made about the same amount of money, and all that good stuff. It's kind of a boring data set. Here's what I'm saying is that I just used $80,000 as an example because it's kind of an upper middle income sort of thing. There were 2 of us in my household, my wife and I, and we combined, when I was early on teaching, made about $80,000, and that's about what everybody in the neighborhood made roughly. So when you find the mean, right, of course, what's the mean of 80,000 added together 14 times and then divided by 14? Sure. Yeah, that's going to be 80,000. So everybody average 80,000, right? What's the median? Well, the middle score. Well, there isn't actually a middle, right? We'd actually average the middle 2 scores. Okay, but again, 80,000. And lastly, what's the mode? What's the most frequent score? Well, sure, that's 80,000. So if I asked you, what is a good measure of the center of this data set? Obviously, it would be $80,000, right? Because everybody's making the exact same. So when we talked about measures of center, mean, median, and mode are the most common ones that we're going to use. And they're all the same in this particular data set. Now, I get this question a lot. Which one's the best one? Okay, well, and I usually give my standard statistics answer, which is that depends. Okay, what's it depend on? Well, it depends on what the data looks like. I mean, here in this case, it doesn't really matter which one you give, they all give the same answer. Okay, but it was a sad day on Kiwi Court when my neighbor Hunter and his wife, they decided to move. So, and they lived right next door in house number 8. So next door neighbor, house number 8 goes on the market. And I like to say, suppose that there was a particular resident of Seattle who just tired of the daily grind of driving back and forth to their corporate offices in Redmond, going up and down I-90 and taking the 520 out there to get to their campus where they have their big software company. And so they decide that they're going to, get rid of their fancy home up there, and they decide to move into good old Kiwi Court. Okay, and so now my neighbor, was now the late great Paul Allen. Okay, so what's going to happen is we're going to exchange Hunter and his wife Michelle's $80,000 a year salary for Mr. Allen's salary, which is a little bit different than the rest of Kiwi Court. What do you think is going to happen to our measures of center? Okay. Conservatively, Mr. Allen was making about $40 million a year at that point. Let's just start at the bottom. What's the mode for this data set? Yeah, it's still 80,000, right? There's 13 80,000s and 140 million, so that's 80,000. What's the median? Well, if we line them all up in order and average the middle two, we're still going to get $80,000. Okay, but what's the mean now? In Google Sheets, there's a handy dandy way to find an average. You just type in average. You highlight it highlighted some weird range there. You highlight the range of data that you want to find the average for. Close the parenthesis, hit enter. And notice the mean income of Kiwi Court is now $2.9 million a year. So pretty good deal, right? If I'd have stayed living there, I'd be making $2.9 million a year. No, that's not what that means. Okay, what this is an example of, okay, is that the median and the mode are what we call resistant. They are resistant measures of central tendency. These guys here are resistant. Okay, the mode doesn't change, right? You added one data point that was really high, but it didn't really move the mode. The median is not going to move. Okay, all we did was replace the top 80,000 with another big number, 40 million. So the median doesn't change. The mean, however, is not resistant at all. The mean is very susceptible to the presence of outliers in the data set. It always gets pulled in the direction of the outlier. Okay, and so, when I think about when we were describing distributions before, right? In this case, our data set, like if I were to make a quick dot plot, over here at 80,000, we'd have, 13 dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And then way out here, we'd have one over at 40 million. And what has happened is the mean has been pulled to the right. Okay, so the mean actually drops over here somewhere. That's where our new mean is going to end up. And so this outlier, the presence of that outlier, is skewing the data to the right. Okay, so in this case, what would be the best measure of center if I wanted to know what does a typical home in Kiwi Court make in terms of their annual salary? Well, I'm certainly not going to choose the mean, right? Nobody makes $2.9 million in Kiwi Court. Okay, They make 80,000 or they make 40 million. Okay, so the mean's not a very good choice for a measure of center in a data set that is drastically skewed. Okay, it's better to go with median or mode. Okay, and this is a good example because when you start talking about income, it's drastically skewed. Okay, in the United States, we have one of the worst disparities of income distribution in the world. And it's so far skewed to the right. It's unbelievable. I have a video that we'll watch in class that kind of explains what I mean by that. Yeah, in fact, they don't usually talk about mean income in the United States. They talk about median, okay? Because the median in the case of that skewed data set is a better measure of central tendency. So those are the three. I think you remember them from before, your math classes before, probably talked about mean, median, and mode. We're just adding to this discussion a little bit about the fact that, mean is not resistant to outliers, median and mode are. So that's why when we talk about a data set being skewed, it's always skewed in the direction of the outlier, because that's where the mean is going to get pulled. If it's a low outlier, it gets pulled to the low side. If it's a high outlier, it gets pulled to the high side. And that's how mean, median, and mode help describe center in a data set. Let's talk about medians, and then we're going to talk about quartiles, because we're going to be coming up with something called a 5-number summary for our data. Now, my first data set here, I have commute times in North Carolina. So we have a random sample here of 15 commute times, and I did put these ones in order. I didn't order the ones for New York. I'll show you how to do that here in a second. When we have these data points here in order, and I want to find the median, what I'm going to do is, with 15, obviously, okay, we just go 1, 2, 3, 4, 5, 6, 7, 8. Okay, 1, 2, 3, 4, 5, 6, 7. There's 7 above and 7 below. So that's our median. Well, when I start talking about quartiles, guys, all I'm talking about is the median of the lower half and the median of the upper half. It divides the data into quarters. Okay, well, if there's 7 data points here in this lower half, then the median of those 7, 1, 2, 3, the fourth one, okay, that's the first quartile. We're going to call that, oops, that's supposed to be a letter Q. That doesn't look like a letter Q at all. That's going to be called Q1. Okay. And then our upper quartile, 1, 2, 3, 4, is the median of the upper half, and that's going to be called Q3. Okay, so hopefully you followed that. If not, rewind the tape, take another look. Rewind the tape, like this is on tape, sorry, rewind the recording. Q1 and Q3 are the 2 quartiles that represent the lower quarter and the uppermost quarter. Median, actually, then, as you may have noticed, could also be called Q2. It's another name for it. Okay, and so what we get out of these, combine that with the lowest value, that's the minimum, and the highest value, which is the maximum, you get what's called a 5-number summary for your distribution. See? 1, 2, 3, 4, 5. And the beauty of the 5-number summary is it's exactly what you need to make one of my favorite graphs, the box and whisker plot for our data set. So let's take a quick peek at how to make that box and whisker plot. So I'm going to bring my whiteboard back. Oops. First of all, I got to get a mouse, and then I'm going to bring my whiteboard back. All right. And so just a reminder that our 5-number summary for this data set, we had the min of 5. We had Q1, which was 10. We had the median, which was 20. We had Q3, which was 30. And we had the max, which was 60. So these are the 5 numbers that we need for our 5-number summary. And then what we're going to do is I'm going to have a horizontal axis. Okay, so somewhere I'm going to have a horizontal axis. Your book draws these vertically. Okay, that's fine. You can have a vertical one. It's totally okay. And then all I'm going to do is just number this off. So let's see here. Let's have a different color here. So we'll have, okay, here's 5. Here's 10. Oops, here's 15, 20, 25, 30, 35, 40, 45, 50, 55, 60. All right. Now, I apologize for them not being perfectly vertical. I know that's probably annoying for some of you, and I apologize. And I'm going to label this. This is the number of minutes for the commute time. And then what I'm going to do first is I'm just going to put some dots up here. Okay, this is 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60. And I've got a dot here at 5, dot here at 10, dot here at 20, dot here at 30, and a dot out here at 60. And the box is made by connecting up the 2 quartiles. That's the box. For the box and whisker plot, this needs to move forward just a smidge. There we go. The whiskers connect the box up to the min and to the max. And then the last thing is in the middle of the box, we draw a vertical line through our median. Oops, there we go. And this is a box and whisker plot for the commute time for commuters in North Carolina. Okay, great graph though, because each part of the graph represents 25% of the data. Okay, this upper whisker shows how spread out 25% of the data is. Let me get my drawing tool here. This is 25% of the data here. That's that upper quartile, that's Q3. Okay, this little whisker over here, that's 25% of the data. So you can see how much more compacted that one is. The upper whisker is really spread out. This part of the box in here, this is 25% of the data. This is from Q1 to the median. And this upper part of the box, this shows us where another 25% of the data is. So the box whisker plot's really great. It shows, hey, look, 75% of the data is between 5 and 30 minutes. Okay, so most people are commuting less than 30 minutes. There is this upper 25% that goes all the way to 60. And if you remember the data set, that 60 was only one person. So my question is, could that be an actual outlier? Seems like it, right? Seems to be outside the realm of the possibility of our data set. Well, to actually formally define outliers, we'll come back to this at the end. Hopefully we have a little bit of time for that. We will come back and take a look and see if in fact it is an outlier situation. If it is, I have some equations that will help us define whether that is an outlier or not. All right, let's go back to our data here. I also included the, oh, there it is. I also included the commute times for some folks in New York City, New York State. And as I mentioned, they're not in order. So one of the things with spreadsheets is sometimes you want to put that in order. So you can sort the range from A to Z, and then you can see now they're in order from 5 up to 85. Okay, so now that makes it easier to find the median. You notice we have 20 data points though, so there's not actually a specific median. We have to average the middle 2 numbers. So let's go over there and say, well, okay, if this is data points 1 through 10, And then, so there's, 1, 2, 3, 4, 5, 6, 7, 8, 9 data points. And then we take 1, 2, 3, 4, 5, 6, 7, 8, 9 data points. So the middle two numbers, you average those two. So you take 20 and 25 and average them, you get 22.5. That's the median for this data set. You may notice that that's not really in a possibility, right? We had them in whole minute increments. Okay, the median might not be a data point that's actually in your data set. Okay? The mean might not be a data point that's actually in your data set. If we go back to Kiwi Court, right, we got 2.9 million. Well, nobody was making that in our data set. That's okay. The mean doesn't have to be even possible in your data set. Neither does the median. The only one that is for sure going to be one of your data points is the mode. The mode has to be in the data set because it's the most frequent one. But the other two measures of center, they're mathematical. So they don't necessarily have to be even possible. So in this case, yeah, 22.5 is our median. So I forgot to mention when I put them in order, you noticed I went ascending, and it put the words at the end. The commute times in New York came down to the bottom because the rest of it was numerical. So you can put it back up there or not. It doesn't really matter when you're just working on the rough draft of the data. So, all right. So that's how you find a median of the middle data set. A couple of measures of spread. Okay, so now let's talk about how do we measure spread. Okay, because when we're talking about SOCs, right? We're talking about, shape, outlier, center, and spread. Okay, well, previously, like last week or earlier this week, we were using range, and range is definitely a measure of spread, but it's not all that useful, to be honest. Okay, there's a couple other ones that we're going to talk about now. There's something called the IQR, okay, and that means interquartile range. It's the range between the quartiles. Okay. If I were to go back to this data point or this data set for the North Carolina commute times, what is my IQR? Well, if you look at your data set there, IQR, just figure out how far is it between 30 and 10. You subtract them. And of course, that's 20. So another way we could measure spread is using the IQR. Still, it's not, I mean, it's better than range. Range in this case is 55. The IQR is 20. But that's not really the best way to describe spread either. I mean, it's okay, it works, but there's actually an even better way to describe spread. And that's the next part of what we're going to look at today is how do we define spread using something called the standard deviation. And so what I want you to think about for standard deviation, if we have our data points and we look at them on, say, a dot plot, standard deviation is trying to average out on average how far away from the middle are the data points. Okay, so on average, okay, how far are the data points from the center? And in this case, the center we're going to choose is the mean. Okay. Now I just got done telling you why why the mean might not be the best choice, right? And yet standard deviation always uses the mean. Well, that's because the fact that we have a huge outlier will show up in the standard deviation just in terms of how large the standard deviation will turn out to be. Okay, so again, we're thinking about the average deviation or distance from our data points to the center. Let's go over to the data sets, and I have another data set for you. And we're going to take a look at this one. Now, this is just a random set of data. Okay, so we're talking about standard deviation now. And these are our data points. This isn't a column of standard deviation. These are actually just the data points. Let me change that because that looks a little weird. So this is the data itself. I meant to title this how to find standard deviation. So let me insert that row above. There we go. How to find standard deviation. Okay. And so what we want to try and do is figure out, like, on average, how far are these data points from their center, and the center we're going to use is the mean. Well, what you might be tempted to do is say, well, okay, here's my data points. How far away from the mean are they? You know, so I took the data. Here it is: 1, 3, 4, 4, 4, 5, 7, 8, 9. These were they had a context here. Hang on. This is the number of pets owned by a randomly chosen group of 9 American children. So, like, one child had 1 pet, 3, 4, 4, 4, 5, 7. One child has 9 pets. Hopefully they live on a farm or something with that many pets. Or maybe they're all fish. I don't know. And then that begs the question, are fish really pets? I don't know. But anyway, we won't get into that discussion today. Those are our data points. So on average, okay, the mean number of pets for these 9 children was in fact 5. So if I want to know on average, then, okay, how far are the kids' number of pets away from 5? I found the difference. So, like, this kid has 1 pet, so that's a -4 units away from the mean, right? If you go 5, you go 4 to the left, there you are. This kid, second kid, has 3 pets, so that's a deviation of -2 from the mean. So to find this difference from the mean, all I'm doing is I'm taking the data point and subtracting. This is the data point minus the mean. And what we might be tempted to try to do here, guys, is to find the average of this then. But here's the problem with that. When I go to add this column up, look just in your head real quick. -4 plus -2 is -6, plus -1 is -7, plus -1 is -8, plus -1 is -9. Okay. And look, 4 plus 3 is 7 plus 2, that's +9. -9 plus +9, we get 0. Okay. And this will happen no matter what. Every data set. Okay. I could go in here and I could change the number of pets for any one of these kids, and we're going to get the same exact thing. Okay. If I were to say, oh, look, the kid with the bottom number of pets, right? Now he's got 2 pets. Okay. Well, that changes the mean to 5.11 pets. And now all my deviations change, but I guarantee you, I'm just going to go over here, guys, and show you a command. This is the equals the sum. And I'm going to add up this column real quick. Look, it's 0. Let me put that kid back to 1 pet. Oh, look, the sum is still 0. It's going to keep adding this column up no matter what I do. Oh, this kid right here has, 14 pets. Okay, great. Well, the average went up to 5.5, but the sum is still 0, guys. This cell is always going to be 0. And if you take 0 and divide by the number of data points we have, you're always going to get a standard deviation of 0. So that's not how you actually find standard deviation. Now, that is my attempt to sort of avoid the question that always comes up when I show the actual equation for standard deviation. Because to actually do standard deviation, okay, we have to make these so that they don't always add up to 0. That's a problem. Okay, how could we do that? Okay. How can we get it so that the sum is not always 0? All right, so some of you are probably thinking, you could do an absolute value, and you could. But what we actually do is take that distance and we square it. Let me put our kid back to 9 here so that they're easy. I'm just going to take that number and square it. And I'll do that for all the data points. There we go. You see, what I've done is I've created a list now where everything's positive, so that when I add this list up, it won't be 0. Okay. So that leads us to the equation then for standard deviation. Now the symbol for standard deviation is a lowercase s. Okay. And here we go. There's that Greek letter sigma again. So you take the difference between the data point and the mean, okay, that's these guys, and you square them. That's these guys here. Then the sigma, remember the sigma means add them all up. And then we're going to divide by n minus 1. N is the number of data points. Okay. So in this particular case, guys, what I would say is I'm going to add them all up. Okay, this whole column right here where I've squared them. Okay, that's 52. And then I'll take that 52. Sorry, I'm getting a phone call there. Take that 52, divide by n minus 1. So remember, I had 9 data points. So n minus 1 is 8. Okay, 6.5. And then I'll take the square root. SQ. Sorry. I'm getting that phone call. It just won't stop. Square root of our number. And we get a standard deviation of 2.54. Let's say 2.55. That's standard deviation. Okay, it's the square root of the sum of the deviation squared divided by n minus 1. See, the square root undoes the squaring that we did. And that's why we can't use absolute value, guys. There's no way to undo the absolute value. Okay, so if you're thinking, well, I really think we could do it with absolute value. Yeah, you could, but there's no way to undo that. Whereas if we square it, we know we can square root it. And that would give us what we call standard deviation. I'm doing okay on time, so I'm actually going to go ahead and go and talk about outliers now. But before I do, I just wanted to reiterate that standard deviation should be the method that we are using for all of our descriptions now when we want to describe spread, if we can use it. If they just give you like a histogram with bars and stuff, it might not be possible to come up with the actual standard deviation. So maybe then we do range or something like that. But if we can, and in most cases we can, we want to use standard deviation to talk about the spread. So on average, if I randomly chose a kid, okay, we would expect them to have an average of 5 pets, but the average kid deviates from that by either plus or minus 2.5 pets. So I know, again, 2.5 pets, like how do you have half a pet? Maybe that's what the fish is, I don't know. But you could say that that's what we would expect to have happen. On average, the kid will have 5 pets, but we wouldn't be surprised if it deviated by as much as 2.5 pets, because that's the average deviation from the mean for our data set.